Hello everybody. Alright, we're going to dive into a pretty interesting topic here. This is the topic of differentials. It's basically the version or the area of calculus in which we're going to do a lot of approximation. So I'm going to draw a picture of the pretty standard graph here, one that we're accustomed to seeing. So here's a function, and we can call this f. And then we're going to identify a point. I'm going to call this x. Right here, and then we're going to draw the tangent line to the function at x. Right, so it's going to look sort of like that. And so we're going to define a couple of basic terms here. We're going to go a little bit to the right. We're going to call this x plus h, right, where h is some pretty small number here. And I'm going to draw some dotted lines here so we can see what's going on. And so I think this is enough to define the basic things that we need to define here. So first thing here that we already know from previous lessons is that we use the symbol dy dx to indicate the slope of the tangent line at the point x. Right? So we're going to spend a little bit of time in this lesson really talking about what the dy and the dx really mean. Okay, and here's an old one from algebra. Right? So we tend to use the symbol delta y, right, delta y right here, to indicate the vertical change in the function from the old point x to the new point x plus h. So I'm going to highlight this in color here so we can see it. Notice the function is the one that bends. So if you want to see how it changes, it's this little piece right here in red. So we'll highlight that. So as you go from x to x plus h, this is the vertical change in the function. So in red here, we could call this delta y. Right? It's just that, that change in the vertical direction. So something here in mathematics that is different, we have a new thing that we're going to define here, and it's very, very subtle because it's very similar to the delta y, is something that we're going to call dy. And dy here is the namesake of the section. This is the differential of y. So dy here now is the vertical change, similar to delta y, but it is the change in the tangent line from the old point to the new point. So you can see if you look in the graphic that the dy is a little bit less than the delta y. So I will highlight this in green in a different color so we can see it. Right, so it's just this little part here. So this is what we would call dy. So dy here we call the differential of y. So I'll write that down here. So dy is the differential of y, and that is more or less the topic of this lesson, what we're going to talk about. So something you can infer from looking at this picture, as long as the movement to the right, the horizontal movement, is small, you can tell that dy and delta y are nearly equal. Right? So you could tell here if you were to shrink the value of h, then you can look in this part where the function and the tangent line nearly agree. They almost look the same. So that's the big piece that we're going to use here in terms of estimating. So I'm going to make that a little bit more formal now. We can write a statement down. So we can jot it down this way. So as long as the movement to the right is small, right, so for h small, you can see in the diagram that delta y is very, very close to dy. So the reason this is significant is that in most applications, it's easier to work with a straight line than it is a complex function. So we're going to take advantage of this in trying to calculate this instead of this. So computing the actual change in the function can sometimes be cumbersome. But computing the change in the tangent line is a fairly straightforward thing, especially if the movement, right, if the h value is very, very small. So we'll take a minute here just to talk about how we calculate this thing dy, and then we'll look at an example of this. So it is pretty straightforward here, because you go back to the first thing that we talked about. So this is how we understand the derivative, right? dy dx is equaling f prime of x. So this dx here coincides exactly with the horizontal movement that is equal to h. So if you want to calculate the differential, we simply multiply both sides by dx. So here we go. So the differential of y is equal to f prime of x, and then dx here. So this is how we can calculate that vertical change in the tangent line, which should be very close to the actual change in the function as long as the dx is small. And another thing to add here, right, is that the dx is equal to the h. So these are just two different ways of writing the exact same thing. Sometimes you'll see this written as delta x in textbooks. Sometimes you'll see it written as h. So what we'll do here is a simple comparison problem so we can get a feel as to what it looks like to calculate these two things. So let's look at a problem here. This one should be pretty straightforward. So this example is saying let's take this function y equals x cubed and let's compare these two values. Let's compare the change in the tangent line with the actual change in the function. And notice we're going to start when x is 1 and we're going to move a very small amount to the right. So we're going to start at 1 and then add on top of that 0.1. So the movement here is really from 1 to 1.1. So we'll do both calculations here. So we're going to use this function here. So in this example, right, dy dx is going to equal 3x squared, because that's the derivative. So we can very easily calculate the change in the tangent line. dy is 3x squared dx, right? And remember, this is going to be our dx, right? The h is equal to 1/10. So at this point, you simply insert the information right in here, and that should be it. So x is equal to 1. And the h, or the dx, is 1/10. So this we can calculate basically in our head. So this will be 3/10, so 0.3. So the interpretation here is if we move on this function from 1 to 1.1, right, adding this number on top of that, then the tangent line is going to change vertically by this much, right, a very small amount. So what we can do now to check this out is to also calculate the actual change in the function. So we're going to calculate delta y. So I'll move this over here. So this will be the second part of the task. So the actual change in the function is like the new point that we've arrived at minus the old point. So this will be f of x plus h, and then minus f of x. So you might recognize this is the numerator part of the difference quotient. So here x is 1 and h is 0.1. So the way we're going to calculate this is f of 1.1 minus f of 1. So this is going to give us the vertical change in the function. And notice when we write down f for this part, we have to use this function here, right? Y equals x cubed. So to calculate this part, this is going to be 1.1 cubed minus 1 cubed. So this calculation, in some sense, involves a little bit more manpower because you have to calculate this, whereas this is a little bit easier to calculate. So you can crank this on a calculator here. And this is the value that you get here. So you get about 3/10 again, right? 0.331. So this value on the right represents the actual change in the function, right? As you move from 1 to 1.1, this one represents an approximate change. So this one here is calculating the change in the tangent line. So notice as long as this value is small, 1/10, you expect these values will be comparable, right? You could probably use this one here to estimate what you would, or I should say you should use this one here to estimate what you would normally get in this case here. So I want to show a couple of graphs here so we can make some sense of what just happened. So you can look at y equals x cubed. This is the graph here that's in red. and then you can see the tangent line to the function at x equals 1. So we can tell here, as long as you don't move that far away from 1, the tangent line does a very good job of estimating or approximating the bend in the function. So the key here in this setting is that this is going from about 0.5 to 1.5. This window is very, very small, from 1 to 1.1. So to show you what that looks like on a finer scale, the picture here looks awfully different when you look at this. So when you look at this graphic, on the right-hand side this is 1, and left-hand side we have 1, and on the right-hand side we have 1.1. And you'll notice the difference in the red and the blue functions is very, very small. So you can see the calculations that we went through and did. The change in the tangent line, we ended up with 0.3, and that is this value here that you can see, the blue line. But you can see the change in the actual function is slightly bigger because the red curve is slightly above the blue line. So when you look at this diagram, you can really see both of the calculations here. So on a small scale for this small horizontal change, it would be sufficient to use this value, right, 3/10, as an estimator for the true change in the function. Alright, so one more basic thing to talk about here. And this is going to build off a formula that we already had up here. So that's the actual change in the function. So this one here. So the change in y, right, delta y is equal to the new value minus the old. So what we can do here to start estimating is we know that dy is going to be pretty close to this. So dy we can say is about equal to this. Right, provided that we have a small h, and then what we can do here is to swing this over to this side. Right, we're going to bring this over here, and then we can rewrite this formula. So I'm going to write it going this way here, starting with the f of x plus h. So it'll look this way. So f of x plus h will be about equal to dy, right, and then plus f of x. So this is a nice little approximation formula, because what it's really telling you is that if you want to calculate a function value like this that is slightly away from a value that might be convenient, something like that, then all you have to include as the disturbance measure is the differential. So you might want to calculate the function not at x, but at x plus something pretty small. And this formula is telling us that all you have to do is to calculate it at that value, f of x, but also include the differential. So the way that this is typically written in math books, and it should match exactly what we have up here, hopefully it will. So f of x plus h is about equal to f prime of x h, right? So this here is exactly the formula for dy. So remember, dy dx is equal to f prime of x. So if you solve for the dy here, you'll have f prime of x dx, and dx and h are the same, and then plus this function value here. So this can be used to calculate values that are less than convenient. So I'm going to show an example of this just to see how it works. And this, believe it or not, this formula is used a lot in calculators, right, for programming purposes. So I'm going to leave this up here. And let's just go through a basic example. So we'll go through this one here. So what we'll do is we'll try to estimate this number, the square root of 9.3, and we're going to use this concept, the concept of differentials. So what you might notice right away is that the function involved is the square root function, and the convenient value would naturally be 9, right? Because the square root of 9 is an easy one to calculate. This one is slightly away from 9, but you can tell your delta x or your dx is a very small number. So what we should do here is to start writing down the important information that we need. So the function at play here is definitely the square root function. That's what we're going to have to work with. And the convenient value would be 9, because that's easy to compute. And then our dx, or our h, is that movement away from 9, right? And that would be 3/10. So notice when you add these two up, right, you end up at 9.3. So the other thing that we need here naturally is f prime, so that's something we should calculate. So the derivative here, we would think about this as x to the 1/2. So we would get 1/2 x to the negative 1/2, and then you would rewrite that. So this would be 1 over 2 square root of x. So at some point we're going to need that, right, when we throw it into that formula. Alright, so let's see what this looks like. I'll move this here. So we're going to calculate it. So now we're going to do f of, right, 9 plus 0.3. We're going to calculate that. So this here is going to be approximately equal to the derivative, which is right here, but it's calculated at x, and x is 9. So I'm going to write down the derivative, 1 over 2 root 9. Right, so I'm borrowing from that formula. And then we have the h, which is 3/10. So this is 0.3. And then what we're going to add to that is f of x, right? So we have f of x right here, but x is 9. Okay, so this, what we see here in blue, is an exact application of this formula up above. And that's using all of the information below. So I'll clear some space there. And so if you think about what this left-hand side is, this is f of 9.3. And that's exactly the thing that we're trying to compute, right? The square root of 9.3. So root 9.3 is about equal to this right here. And you can interpret this as 3 as being right here, and then you have to add on this little element here. And this is exactly how you can approximate it. So if you just figure this out, this will be 1 over 2 times 3, and this is 3/10. So I'm just simplifying here. So this is pretty simple math, right? So this will be 1/20 that we have here, and that's what we have to add on to 3. So this will be about equal to 3.05. And that's the big connection to make here. So the thing that we're trying to calculate, right, this is the square root of 9.3, and what we have found, you can check on a calculator, it's about equal to 3.05. So this is the way that you can calculate this simply by hand by using this concept, right, that concept of a differential.